What a beautiful day. You step outside and you feel the warmth of sun on your skin. Just look at this bee enjoying the scent of the blooming petals. And you feel the same, with no stress and with no worries. So you close your eyes and breathe the fresh morning air. The grass sways lazily under a sky so blue, it feels like even time itself has slowed down. Just you, nature, and the comforting stillness of a world untouched by chaos. You say now to yourself with the confidence you never had, nothing in this world could break this peaceful moment. I wonder what is a Turing machine, you say to yourself. Is it useful for computational complexity? And now you would ask me a very natural question. Why would someone ever ruin this moment with such questions? And I would agree with you. I don't know. But I know that we call these people computer scientists, and luckily for you, you're about to become one. Even though this question about what is computation is really interesting itself, the definition of computation isn't something very difficult to see, because we can define computation simply as all the steps between an input of a problem and the output or the solution of this problem, meaning that everything that happens between this step and these steps, all these small steps that happen here, are called computation. And okay, maybe it seems really abstract about what is a problem, what is the solution of a problem, and also why do we care so much about this process, the computation, because what is more interesting is often the solution, the output. But if we think about it, during all humanity, we wanted to solve the problems in the most efficient way, without having too much steps here, without doing it in a bad way, and just wanting to find the best way to not lose too much time, energy, and even money. And so that's why we care so much about this computation process, because we want to do it in the best possible way. And we want to study, okay, I have a problem, and the problem can be basically anything. How fast can I solve this problem? Using simply something very human, or using even a computer. How fast, how efficient can be my problem solving? And for example, we can take basically anything as a problem, as I said. So for example, if you want to have a very simple problem, it can be simply summing two numbers. Let's say that we want to solve just two random numbers. We want to sum these two numbers. And even though we can do it just in our head, because it's not very big numbers, what happens now if we have really big numbers with, I don't know, 100 digits each? It's possible, but it's really useless to spend all our time and effort doing it in our head when we can just have a very easy algorithm to just use a paper and write on it. And basically in school, we were taught a way of doing this thing. And we just write the two numbers in a table in such way, and we just sum the digits themselves like this. So here we have 2 plus 1, which gives us 3, 7 plus 6, which gives us 13, and so it's the 3 is here, and we put a 1 here. And so now we have 1 plus 8 plus 9, which gives us 18. Again, we put a 1 here, and we have 1 plus 2, which gives us the final number. So this was the input, this is the output, and everything what happened here is again the computation. And we see that all the problems can be solved in this way, meaning that we have an input and we have an output, and between the two steps, between the input and the output, we have the computation. And depending on how smart we do it, we can make the computation smaller and smaller. And sometimes we can make it smaller, and sometimes we have a limit. We can prove that we cannot do it faster. And proving such things is really the goal of what we call computational complexity. But before going to the definition of what is computational complexity and Turing machines, let's try to see another problem to convince ourselves. For example, let's now assume that I have a bit more difficult problem. For example, I can have a bag with a lot of blocks inside with numbers written on them. For example, I have a block with 2, one with 10, one with 3, one with 5, and one with 8. Okay, now the task is simply, please, I want that you sort these blocks for me. And we can sort them in any order that we want, but here we will say that we want to sort them in an increasing order, meaning that we want to have a list of these blocks from left to right, from the smallest to the biggest number that we have. And here, one way of doing it is simply, well, okay, I have my blocks, and first I look for the smallest one. And here the smallest one between all these numbers is just this one, the 2. So we can just take it and put it here. Okay, I place my first block, and now let's continue. We can continue with the left blocks here to see which one is the smallest again, without the 2, of course. And now the smallest one is clearly 3. So we just take it and put it next to the 2 one, and we continue. So on, so forth. We see that the next one is 5, then the next one will be 8, and the last one will be 10. And at the end, we have a sequence. We have a sequence of blocks that are sorted in increasing order. And so, again, these blocks were the input. All this process of looking for the smallest thing, for the smallest number, is called the computation. And the output here, that is the sorted list of blocks, is called the output. And again, before we saw that we have an input here, we have an input, an output, and between them we have computation. Here it's the same process. We have an input, we have an output, and between everything we have a computation. And basically, this kind of convinces us that any problem can be seen as just having an input and then having like some place. Here I have my screen where I can write everything I want, some scratch paper where I can just solve the problem, and then I have my outputs. And any problem can be seen as this. And this framework, this way of seeing things, is exactly what does a Turing machine. And so a Turing machine is just a way of seeing things in a very mathematical way, meaning that, okay, I have a place for my input, I have a place for my computation, and I have a place for my output. And then my computation is just a combination of some rules that I do to manipulate my input, to manipulate my computation, to find the output in the best possible way. And we need this mathematical definition of what we can call a computer, a modern computer. We want to study complexity. And complexity is simply how much steps, how much rules do I need to solve my problem in the best possible way. And because this notion is really mathematical, we need a very mathematical framework too. We need a very mathematical model. And this model is exactly, again, the Turing machine. So now, this leads us to the following question. What is a Turing machine? Now, answering to this question is not as easy as answering to what is computation, but we can do it. And basically, for a bit of history, who invented Turing machines? Well, as the name says, is this guy named Alan Turing. This guy invented Turing machines during the Second World War. And the idea was, okay, I have problems and I want to solve them using one magic box in some sense. I want to have like a box here. And we say that, yeah, it's a magic box. And I want that, okay, I say to it some instructions to configure the magic box. And after applying the instructions, I want to have an input X. And I want that it outputs some solution. Okay, and this magic box here is the fundamental idea behind the Turing machine. And basically what this magic box does is just like, as we saw before, it has an input, some computation, and some outputs. The computation is just a sequence of rules to apply to the input to create the output. And these rules, again, these rules are defined by their instructions here. And basically the idea is just the idea behind the modern computer. Because with your computer, or with your phone, or anything, you can simply just have programs, which are the instructions, and they will do what you want. But you have only one computer. You don't have one computer for each single task that you want. You have one to do everything. And this computer that you have is the dreamt magic box that Alan Turing, this guy here, was thinking about this kind of process. And okay, even though Turing machines are not how we create computers now, we don't create Turing machines in the most formal way to create programs or to simply program anything, but it's a very mathematical definition of how a computer works and how basically any simple algorithm can be, let's say, generalized. And even though it's not very important to see what happens behind, it's really interesting to see what is the formal definition of a Turing machine to understand why it models mathematically the computation in a very efficient and clever way. So now let's be a bit formal. What is a Turing machine? As we saw, it consists on an input, scratch paper to write anything during the computation, and in an output. So there are a lot of definitions of what is exactly a Turing machine, depending on how much space do you allow, depending on how you want to read the input, depending on a lot of little parameters. But the definition itself doesn't really matter in most of the cases. So we will just stick to the most classical definition. So we will focus on the classical definition, which is the K read and write sequential read Turing machine. Okay, maybe it seems like a lot of weird words, but we will define them right now. So when we talk about tapes, it's simply assume that it's just a lot of paper that you have where you can write things in an order. For example, here you first have the input tape, and it's just a big piece of paper with some squares in it where you can write things. For example, the input can be, as we said before, the two numbers that we saw. So it can be the number x and the number y. And we want, and here, nothing. And we want to solve them. And so, to solve them, we have even more paper. But here the inputs, we don't need to write in the instructions. We don't need to write in our task. So here we say that this tape here is read only. So you can only read it. But hopefully we have other tapes where we can write things. Basically our huge scratch paper. And we say in our definition here that we have, let's keep it in black. We have K tapes. So we have K of them when we can basically read, of course, but we can also write in these tapes. So here we can imagine that it's just like a big scratch paper when we are doing this thing. For example, to sum, we want to solve one number with the other one, and then it gives us something, and so on and so forth. And then we can have something here, something here. We can do whatever we want. But this last tape here is very special because we call it the output tape. Meaning that when the computation is done, the result is written in this last tape. And okay, now this is the elements of how a Turing machine works. But to be even more formal, how do we even read things? How do we even know where to write things? Well, it depends again on what definition you choose, but here we use the sequential read or sequential write to. So meaning that for each tape, you have like a place. We always begin at the first place, And we say that here I'm reading this place, I'm reading this place, I'm reading this place. And I can write this, I can erase this, and I can write something else. If I want, I can just write here, I can write 7 here. And I can continue. I can say, okay, I don't want to be here now, I want to be here and to deal with this place, so on and so forth. And so we call this the heads of the tapes that says, okay, now I'm reading or writing in this place. Here, of course, it will only be the place where you are reading, but you can only go one cell at a time. So I can be like, okay, this is one step, I want to read this thing, then I want to read this thing, then I want to maybe go back and read this thing, and each direction that you choose is one step. And so all this computation is only a sequence of rules, and the rules, we just define them, is simply just to read, to move the heads, to write, or simply to stop. And when we stop, the output should be written here. And even if it can seem really simple, these 4 rules that are allowed can be used to define any possible computation that you want. And okay, now it's a lot of drawing, but now that we know a bit the image of how everything works, we have even a more formal way of defining things that I will just explain now. So now that we know everything of this, a Turing machine can be defined as a tuple, meaning that it's just some objects together that define what is the Turing machine completely. And the tuple is a set of states that we call BQ, an alphabet that we call sigma, a transition function that we call little delta, a starting state that we call Q0, and first, Q0 needs to be inside of all the states, and final states. And all the final states needs to be inside of the states. And we could just say that we want this thing and we require to have special states like this, but the convention is to write a Turing machine with a 5 tuple as such. And what is the final state? Well, it means that each time that we reach a state that is in F, we stop and we say, okay, we're done. Now you can read the output and it's my solution. And Q0 is just, okay, now I start in this state. And we cannot go back to this state again. It doesn't make sense. And now let's more take a look about the other things, which are the alphabet and the transition function. Well, the alphabet is really simple. Often in computers, the alphabet is just the set 0, 1, which means that a computer only sees a bunch of 0 and 1s. But for example, in our summation problem, when we wanted to solve sum two numbers together, like this, well, the alphabet is simply all the numbers between 0 and 9. So in this case, well, sigma was simply 0 up to 9. And the alphabet can be anything, really, as long as it's a finite state. More precisely, sigma, the size of sigma needs to be less than the infinity. You need to be able to count and to be able to say, okay, I have only a finite number of elements in my alphabet. But often we can just say that sigma is just 0 and 1, and it's equivalent because we can kind of translate everything that is here to everything that is here. For example, here we can just use the binary encoding of each number to simply translate it to this alphabet. And okay, now the most difficult thing here is this little delta. So to define exactly what is our transition function, let's take a look again to our drawing here. We can say that, for example, we are, I don't know, we are in any possible state. Let's say that we are in the state Q1. And okay, we are in the state Q1, and currently the elements that are read on each tape are this one, this one, or no, this one, and this one. And basically, everything here defines the state of our machine, because we are in state Q1 and we are reading all of this. So only knowing all this information, we can know what is the next step to do. So let's go back to our formal mathematical definition. A transition function is just something that will take a state and that will read all the k plus 1 elements, because we have k read and write tapes, but we also have the input tape, and it will map this thing to a new state, to things to write if we want to write something new at this place. Of course, not k plus 1 anymore, because the first one is not writable. And also, we want to say if I go left, if I go right, or if I want to stay. And again, this is for k plus 1. So basically, depending on which state you are and on what things you are reading now, the transition function will tell you that the next step will be, now you will be in a new state, you will write new things in the tape, and you will move your heads in the following manner. For example, here, if we have only one tape, you can say that it maps to, for example, I don't know, to LR, meaning that your input tape's head will move left, and the read and write tape will move right. And we can also stay if you want. We can also not move. For example, if here we have S, we don't move anymore. But okay, it's very mathematical and we won't take too much time on this thing, but this is the mathematical definition on how a Turing machine works. Simply just, it's a set of rules. So here, the transition function defines exactly how every step occurs. And even though it's possible, I won't translate this algorithm, this computation, into a Turing machine because it's just very, very huge. Maybe I will do a video, an exercise to show how it works. But here you have the mathematical definition of what is exactly a Turing machine. And the complexity of the Turing machine, we will define it a bit later, but the idea is that the complexity is depending on what input you are given, the input that is written on the input tape, the number of steps, the number of times you call this transition function is basically the complexity, the time that you will take, that your Turing machine will take. So basically, a Turing machine can model any algorithm, so it's equivalent to say the complexity of my computation, of my algorithm, is the number of steps, the number of calls, the number of times I need to call this transition function. So basically, if I just have an input and I need to call it, I don't know, 2 times, it's really, really efficient. And sometimes I can need to call it way more times. But we will define it just now. And this leads us to the final question of the video. What is computational complexity? Now we have all the necessary tools to answer the most interesting question of the video. What is computational complexity? But first, why do we ask this question to ourselves? First, because we want to know how good is my computation or is my algorithm. And we saw that to define mathematically an algorithm, the best way of doing it, the best way to generalize it, is using Turing machines. And now we know how Turing machines work, and we have a very good measure on complexity. Namely, let's assume that we have a Turing machine that we often will call M that solves a specific problem. Let's assume that now our Turing machine solves the problem that we set at the beginning of the video, which is just summing 2 numbers. Meaning that if you give to the Turing machine 2 numbers a, b, the result will simply be a plus b. And often we just write the input as x. X can contain a and b. And a very good measure on complexity is the number of calls to delta. So we can define the time complexity of M. We often write it as t on input x, which is the number of calls to the transition function that we call delta. We say that this measure here is the time complexity because it just measures how much time, depending on your input x, here x again is AB, how much time it takes to solve the problem. And here we talk about time, but we don't exactly talk about seconds. We talk about number of steps. But of course, the more steps you do, the more seconds you will also need. And often we just care about the time complexity, but there are other complexity measures that are interesting. For example, we can care also about the space complexity. But here, when I talk about complexity, I will mainly just talk about simply time complexity. So when I talk about computational complexity, I will implicitly talk about only the time complexity because it's the one that we always start with and is the most interesting one. So here we define the time complexity depending on a specific inputs. But the thing is that we're not very interested on the time that it takes for each single inputs. We want to optimize for a general set of inputs. We don't want to optimize our algorithm for just one specific input because we don't know. Like if someone tells us just can you sum these two numbers, you don't know in advance what the two numbers will be. You prefer to have an algorithm that will be good for any kind of number that we will receive as an input. And this is why we don't really use the input itself for the time measure, for the time complexity. We'll more use what we call the input length. So here, we often will write n as the input length, meaning that the number of elements that the input has. And we'll just define this as the input length. For example, if before, in our problem of summing two numbers, our alphabet was something, what's all the numbers from 0 to 9, and our input x is just two numbers, for example, these two numbers, well, here, and the input length is simply just equal to 5, because you have 5 numbers here. Of course, this thing can be a special character, so we can say that it's 6 and that the alphabet here contains like the separation between the two numbers, but we can roughly say that the input length is equal to 5. It's okay. Okay, so this is the input length, and we want to measure the complexity only because of this input length. We're not very interesting again as how is my algorithm efficient with a specific input. We often, and we always actually, write the time complexity as a function of the input length and nothing more. And because, again, let's take another example to make it a bit more obvious what I will say. This time complexity, of course, the number of steps depends, of course, on the input that you're given. For example, if you want to sum two numbers, let's say this and this, it will take some time, okay, and it will require some time and But now what if you have something else like, I don't know, this number and this? It's way easier to sum because you know that a number plus a number that is just equal to 0, it's just the number itself. So here it's super easy. So this is easy and this is harder. So naturally here it will be smaller than if we call this number x and this y, it will be smaller than t of y, of course, but n here is equal to 5 and n is equal to 6. But okay, we can just remove this number and we'll have the same number and we'll have the same thing. So here we can say that n is equal to 5 in both cases. And okay, now we know that the complexity is not the same even if the input length is the same. So okay, we know that this time complexity here can't exactly tell you what will be the complexity, what will be the time, because as we saw here, the two numbers have the same length, but different time. And so here we have different choices. We have actually 3 choices. Either using what we call the worst case scenario, the best case scenario, and the average case scenario. For example, here if my Tn, for example, if Tn can take, I don't know, a lot of steps, like for example n power 3, but sometimes it can take just one step, well, we say that the worst case is this thing here. So the worst case is the maximal over all input that have a size n. Oh, sorry, here again, over all input here, the alphabet could be anything that has size n. This is the worst case. And on the opposite, when here you replace the max with the minimum, meaning that here the best case is this thing, well, here you say that it's the best case. And the average case is just on average, how many steps do you need with this length? And so often we are likely to use the worst case scenario because we don't care if there is one special input that will make everything so fast. Because again, we don't want to optimize for just one specific input. We want to optimize for everything. So we want that even in the worst case, our algorithm is good. So we will often write this worst case. And the worst case here, use what we call the big O notation. And if you don't know about this, I recommend you to look at some videos that explain you what exactly are the big O notation and the other notations. But here it means that roughly, for example, if t of n is equal to big O some function n, it means that in the worst case, it will take f of n time. For example, here it can be n power 3. Okay, and for completeness, I will explain the other ones too. So, the best case, we write it as big omega. And of course, the best case here is 1, meaning that the number of steps is at least 1. And here it's at most f of n. And the average case here, we say that on average, the number of steps will be something that I didn't define. And here, for average, we use the theta, a big theta. And that's it. Now we know exactly what is time complexity, and in general, what is computational complexity. Here we saw that in the most general case, we use this as a measure of complexity. And basically just, we have a problem and we have an algorithm to solve it. And we want to see if we can do better, if not, and how difficult this problem is. And now the question is, why do we care so much about this measure? Well, because, as I said in the beginning of the video, we want to see what problems are really difficult or not. And this time complexity here, that uses Turing machines, is really, really useful to make abstraction of the problem itself, of the algorithm itself, because we only care about the efficiency, the complexity of the problem. And we will see, or maybe you already saw, that it's useful to define some specific classes. For example, there are problems that are really easy to solve, and we call this class of problems the class P, because they can solve in polynomial time, meaning that, for example, t of n, if t of n is equal to, let's say, big O of n squared, n cubed, sorry, well, this lies in P, because it's polynomial. If it's n, it's also in P, but if it's something bigger, like, for example, 2 power n, this doesn't belong to P. And some other bigger classes, this, for example, lies in what we call the exponential class, which means that we can use up to 2 power n or 2 power any polynomial of n, and it's a very, very huge class. But if your problem is in this and is not in P, well, a computer will take a lot of time to solve it if the input length n grows and grows. Whereas if your problem lies in P, well, if your input is really big, it will take time, but it will be really efficient, and it will not grow exponentially. It will grow polynomially. And now you can probably say that you know what is a Turing machine and why it is useful. Maybe it was a bit abstract on why it is really useful, but what can I do? This is computational complexity, and only the more abstract souls like to study this subject. But okay, now you can probably say that you know how to use them, you know how to define them, and you can finally have the peace that you wanted at the beginning. Thank you for listening, and see you next time.